In the relentless theater of aerial combat, where the blue expanse becomes a crucial battlefield, altitude is not merely a number, it is the ultimate, non-negotiable advantage. Smash the like button and subscribe right now if you want to understand the revolutionary engineering that turned the tide of the air war. The fundamental physics of our atmosphere, however, impose a strict and unforgiving rule upon any machine seeking to ascend. For every 1,000 feet a pilot climbs into the sky, the ambient air density diminishes by an approximate 3%. By the time an aircraft reaches a demanding 25,000 feet, the traditional piston engine, the stalwart workhorse of early aviation, begins a profound and terminal decline. Its volumetric efficiency, the measure of how effectively it can draw air into its cylinders, plummets by 50%. The engine does not simply lose power, it becomes anemic, starved of the essential oxygen required for proper combustion. The American military and its engineers recognized this critical limitation, understanding that success in the next global conflict would depend on overcoming this atmospheric chokehold. They desperately required a technological solution to forcibly feed their engines the necessary volume of oxygen, irrespective of the punishing thinness of the high-altitude air. The necessary answer, the key to unlocking the upper reaches of the sky, was not simply a demand for a larger piston displacement, a heavier, more cumbersome cylinder block. Instead, the solution materialized in a far more elegant and revolutionary device, a high-speed, precision-engineered spinning wheel. The fatal flaw of the Otto cycle. The year is 1917. The internal combustion engine, the undisputed powerhouse of the nascent aerospace industry, operates according to the ironclad principles of the Otto cycle: intake, compression, combustion, and exhaust. Yet, this time-honored cycle harbored a fatal, intrinsic flaw, a deep-seated vulnerability tied directly to the vagaries of atmospheric pressure. The very mechanism relies entirely on the ambient air pressure to physically push, or induct, air into the cylinder cavity during the intake stroke. At the benign, dense conditions of sea level, this mechanism functions flawlessly. A robust 14.7 pounds per square inch, psi, of pressure acts reliably to pack the cylinder full of oxygen molecules, enabling a powerful detonation. However, a pilot seeking to climb that same aircraft to a safer, strategic altitude of 20,000 feet, perhaps to evade ground-based anti-aircraft fire or to gain tactical superiority over an adversary, experiences a brutal drop in this crucial pressure. At that height, the pressure falls dramatically to a mere 6.7 psi. The stoichiometric ratio, the scientifically ideal mixture of 14.7 parts air to 1 part fuel that ensures complete and efficient combustion, becomes utterly impossible to maintain. The engine's fuel-air mixture becomes rich, too much fuel for the available oxygen, leading to a debilitating loss of power. The engine, literally and mechanically, begins to suffocate. Dr. Moss's vision: harnessing waste heat. Into this critical engineering vacuum stepped Dr. Sanford Moss, a brilliant and forward-thinking engineer affiliated with the General Electric Company. While his contemporaries and rivals were pursuing the conventional, brute force approach of building ever larger engine blocks and increasing displacement to mitigate the power loss, Moss fixated on a more subtle and overlooked concept: enthalpy, the total heat content and energy inherent within a thermodynamic system. His gaze settled upon the seemingly wasteful moment of the exhaust stroke. When the exhaust valve opens, intensely hot gas, a searing mixture exiting the cylinder at near supersonic velocities and temperatures approximating 1,500 degrees Fahrenheit, or 800 degrees Celsius, blasts out of the engine. For most engineers, this represented pure, unavoidable waste heat. For Moss, however, it represented an untapped reservoir of high-velocity kinetic energy, a free power source. His idea, which would irrevocably change the course of aviation history, was the turbo supercharger. The elegant mechanism of waste recovery. The core concept is a marvel of elegant thermodynamics and mechanical ingenuity. Moss proposed placing a robust, radial turbine wheel directly within the scorching hot exhaust stream. The rapidly expanding high-energy exhaust gases, in their hasty departure from the engine, would impinge upon and violently spin this turbine wheel at immense velocity. This exhaust-driven turbine would then be connected via a high-strength, solid shaft to a centrifugal compressor wheel strategically positioned on the engine's intake side. The compressor, powered indirectly by the exhaust, would viciously suck in the thin, ambient high-altitude air and compress it adiabatically, meaning the process occurs without exchanging heat with its surroundings, forcing a dense, oxygen-rich column of air into the engine cylinders, effectively restoring and even exceeding sea-level pressure. It creates a positive feedback loop of immense power. The harder the engine works, the greater the volume and energy of exhaust it generates, which in turn spins the turbocharger faster, and the more dense air it forces back into the intake. This is, by definition, bootstrapping power. To understand the brilliance of Moss's approach, one must contrast it with the existing technology. Conventional superchargers, such as those used by early German fighters, are driven by a complex belt and gear system directly connected to the crankshaft. This constitutes a parasitic loss, meaning a portion of the engine's hard-won power is siphoned off just to run the compressor. Turbochargers, conversely, are driven by otherwise wasted exhaust gas energy, making them a system of waste heat recovery. The question that dominated early engineering debates was simple. Which method offers superior efficiency and reliability for the demanding conditions of high-altitude strategic bombers? The thermodynamic reality favored Moss's waste recovery approach. If you're finding this deep dive fascinating, give us a follow for more engineering history. The Crucible of Pikes Peak, proving the impossible. While the theory was undeniably brilliant, the practical implementation of the turbo supercharger immediately ran into a colossal challenge, a metallurgical nightmare. The turbine wheel, the heart of the system, had to withstand an operating environment that bordered on the infernal. It was required to spin reliably at speeds exceeding 20,000 revolutions per minute, RPM, while being continuously and directly blasted by exhaust gas temperatures of 1,500 degrees Fahrenheit. In the nascent industrial landscape of 1918, most available engineering metals would either turn molten and drip like liquid at such temperatures or, more insidiously, would suffer from a phenomenon known as creep, a time-dependent permanent deformation that occurs under sustained mechanical stress at high temperature. Critics and skeptical engineers were quick to voice their extreme caution, telling Moss directly, "You are building a bomb." They argued, with genuine reason, that the centrifugal load and thermal stress would inevitably cause the turbine blades to fail catastrophically, shattering into white-hot shrapnel that would lethally imperil the pilot and destroy the aircraft. Moss was compelled to prove his detractors wrong, and he realized such a proof could not be confined to the controlled conditions of a laboratory bench. He needed the raw, challenging environment of thin air. September 1918 became the crucible of this engineering trial. Dr. Moss transported a massive 350 horsepower Liberty V12 engine to the unforgiving summit of Pikes Peak in Colorado. The air pressure at the mountain's peak is drastically low, registering at only 60% of the dense air found at sea level. Without the crucial assistance of the turbocharger, the massive V12 engine choked and sputtered, its combustion suffering, managing to produce a pathetic, power-starved 230 horsepower. Moss and his team then carefully bolted on his prototype General Electric turbocharger. He opened the throttle. The turbine began to scream as it spooled up to immense speed. The gauge monitoring the intake manifold pressure climbed steadily, 10 psi, then 14 psi, perfectly matching the pressure levels of sea level. But then, astonishingly, it kept climbing. The engine did not merely recover its lost power, it decisively surpassed its original specifications. At a challenging altitude of 14,000 feet, the turbocharged Liberty engine successfully cranked out 356 horsepower, a power output exceeding its official sea level rating. Moss had achieved the seemingly impossible. He had proven that manifold absolute pressure could be successfully and permanently divorced from the restrictive, altitude-dependent ambient pressure. The new crisis: thermal management. Yet, just as the pioneering engineers erupted in celebration over this thermodynamic victory, a secondary, equally severe physical limitation immediately presented itself. The very act of compression had an unwanted, devastating side effect. The temperature inside the cylinders spiked dangerously. The engine spark plugs began to melt, and catastrophic pre-detonation, or knock, began to threaten the structural integrity of the entire power plant. The fundamental reason was simple physics. Compressing air drastically increases its temperature. Moss was forcing not just dense, but searing hot compressed air into the engine, which caused the fuel-air mixture to spontaneously and prematurely ignite before the spark plug could fire. Moss had definitively solved the critical airflow problem, but in doing so, he had inadvertently created a severe and urgent heat management problem that threatened to melt the entire engine block into a useless mass of metal. The intercooler and the superalloy. By 1920, Sanford Moss faced a defined, existential problem. He had achieved the technological feat of successfully compressing high-altitude air, perfectly restoring the necessary cylinder pressure. However, he could not, and could never cheat the fundamental, unyielding laws of physics. Gay-Lussac's law, a cornerstone of thermodynamics, dictates that for a fixed amount of gas, pressure and temperature are directly and proportionally linked. By aggressively compressing the thin mountain air, the turbocharger had heated the charge air to a scorching temperature exceeding 300 degrees Fahrenheit 150 degrees Celsius before it even had a chance to enter the engine. Hot air possesses an inherently lower density than cold air, meaning the compression effort was less efficient than it should be. Worse, the intensely hot charge air caused the delicate aviation fuel to auto-ignite, to detonate without the controlled spark timing, a phenomenon that saw the engines literally destroying themselves from the inside out. Moss realized with sobering clarity that to make the turbocharger a viable, reliable technology, he didn't just need to pump the air. He had to find a way to actively freeze it. The elegant and necessary solution was the intercooler, a surprisingly simple yet profoundly effective thermodynamic device that functioned as an air-to-air heat exchanger. Moss positioned a specialized radiator core between the high-pressure outlet of the compressor and the delicate intake manifold of the engine. The searing hot, compressed air flowed directly through the internal passages of this radiator. Simultaneously, the intensely cold, ambient air from the high-altitude slipstream, air that was far colder than the ground air, was strategically routed to flow rapidly over the radiator's exterior surfaces. This created an aggressive and rapid heat transfer. The temperature of the charge air plummeted from a destructive 300 degrees Fahrenheit to a manageable 100 degrees Fahrenheit. The air, now cooled, became significantly denser. The vital oxygen molecules packed tighter together, achieving a higher mass flow rate. The engine immediately ceased its catastrophic knocking and, instead, began to function with the steady, powerful rhythm of a perfectly tuned machine. However, solving the intake temperature crisis was only half of the colossal battle. The most persistent, real-world nightmare was located at the literal back of the aircraft, within the intense environment of the exhaust stream, the turbine wheel itself. As Moss's turbochargers grew in size and power, the exhaust gas temperatures they had to endure relentlessly climbed, reaching levels of up to 1,600 degrees Fahrenheit 870 degrees Celsius. At operating speeds approaching 20,000 revolutions per minute, the centrifugal force exerted on each turbine blade is immense, constantly attempting to rip the blades from their central hub. Standard, available steel alloys would inevitably soften at these temperatures, suffering catastrophically from creep, slowly stretching and deforming like heated taffy until the blade tips grazed the outer casing and exploded outward in a destructive torrent of superheated fragments. Moss recognized that he was in desperate need of a metal alloy that, quite simply, did not yet exist in mainstream industrial application. His search for a solution led him to an unexpected place, a medical invention. Decades prior, a pioneering inventor named Elwood Haynes had created a non-corrosive, extraordinarily hard alloy specifically for use in surgical tools and dental implants. Haynes had christened this alloy stellite. It was a complex, multi-element mixture, predominantly composed of cobalt, chromium, and tungsten. Stellite was infamous for its incredible hardness, making it almost impossible to machine using contemporary methods, and it was undeniably expensive. But, most critically, it possessed the unique and vital property of maintaining its formidable strength and structural integrity even when heated to a glowing, incandescent red. Moss ordered the critical turbine blades to be cast from stellite. The result was a resounding success. The turbocharger could now reliably survive the relentless, hellish environment of the exhaust stream, operating for hundreds of hours without catastrophic failure. I pose a challenge for the technically inclined. Stellite belongs to a highly specialized class of materials known as superalloys. These alloys remain essential components in all modern jet engines today. Do you know the primary element used in the construction of modern, cutting-edge turbine blades? A small clue: the element's name begins with the letter N. The altitude advantage in World War II. With the formidable challenges of thermodynamics, the necessity of the intercooler, and metallurgy, the invention of stellite, finally solved, the U.S. Army Air Corps was ready to move from the experimental phase to the construction of an entirely new class of weapon, the high-altitude, strategic bomber, personified by the legendary Boeing B-17 Flying Fortress. If one examines a B-17 closely, the secret weapon is visible. Tucked discreetly underneath the engine nacelles are characteristic, bucket-shaped housings. These enclosures contain the General Electric turbo superchargers. They were the key technological advantage, the secret that would turn the tide of the air war. The year is 1942, and the air war rages intensely over the European theater. The B-17s, utilizing Moss's invention, began their missions at a strategically advantageous altitude of 30,000 feet. At this punishing height, the air is so rarefied that an unprotected human being would lose consciousness and expire within 60 seconds. The ambient temperature hovers at an extreme -50 degrees. German pilots, flying their formidable Messerschmitt Bf-109 and Focke-Wulf Fw-190 fighters, would desperately climb to intercept the bomber streams. But as they pushed past the 25,000-foot mark, their engines, which relied on the inferior, belt-driven mechanical superchargers, began to run out of breathable air. The German planes became sluggish, their power severely degraded. They wallowed in the thin atmosphere, struggling to maintain a high rate of climb and maneuverability. In stark contrast, the B-17s, force-fed by Sanford Moss's highly efficient exhaust-driven turbos, cruised relentlessly along at maximum power. For the initial pivotal 2 years of the war, the turbocharger provided the Allied forces with unchallenged and total altitude supremacy. This critical advantage allowed them to systematically bomb the industrial heartland of Germany from a height where the Luftwaffe simply could not fight effectively or sustainably. Sanford Moss, the visionary who had wrestled a V12 engine up Pikes Peak back in 1918, was now witnessing his theoretical invention systematically dismantle the Third Reich's industrial capacity from the stratosphere. But the relentless march of engineering innovation could not be halted. The military strategists and engineers demanded more than just high-flying bombers. They now required their fighter escort to match this altitude. The challenge was to take the massive, cumbersome turbo system designed for a 4-engine bomber and somehow compress it and adapt it for a single-seat, high-performance fighter. The result of this ambitious effort was the Republic P-47 Thunderbolt, affectionately nicknamed the Jug. It became, by necessity, the largest and heaviest single-engine fighter aircraft of the entire war. The reason for its immense size and weight lay in its radical internal design. The entire fuselage was essentially a colossal hollow tube meticulously wrapped around an extensive, labyrinthine ducting system necessary for the turbocharger, which was strategically located in the aircraft's tail section. The required plumbing was a marvel of mechanical complexity. Exhaust gas had to be channeled rearward to spin the turbine, and then the compressed air had to be routed all the way back through the fuselage to the engine at the front. Thermodynamically, this long-distance routing introduced significant inefficiencies. Mechanically, it was complex and maintenance-intensive. But in the crucial environment of aerial combat, the system proved its worth. When a P-47 pilot operating at 30,000 feet pushed the throttle forward, the massive turbo spooled up, and the 7-ton warplane could be directed into a devastating high-speed dive onto an unsuspecting enemy below, descending with the destructive force and velocity of a falling piano. Nothing the enemy possessed could effectively catch or outrun it at altitude. The inadvertent birth of the jet age. Sanford Moss had triumphantly mastered the piston engine, allowing it to breathe at any height. However, across the English Channel, another visionary, Frank Whittle, was simultaneously realizing a more profound truth. If one took Moss's turbine and connected it directly to the compressor, and then introduced continuous combustion between the two components, the piston engine itself became redundant. By 1944, the turbocharger had definitively won the strategic high-altitude air war for the Allies. But engineers, now intimately familiar with the turbo's architecture, began to notice a startling conceptual overlap. A turbocharger fundamentally consists of two components, a compressor and a turbine. It intakes ambient air, aggressively squeezes it, and utilizes the engine's exhaust gas to spin itself. The only component conceptually missing from this assembly was the intermittent, reciprocating piston engine in the middle. Sanford Moss had devoted his entire career to helping the piston engine breathe efficiently, yet he had inadvertently perfected and built the precise, high-temperature components that would soon render the piston engine fundamentally obsolete in high-performance aircraft. In 1941, the United States government received the highly sensitive, top-secret plans for Frank Whittle's groundbreaking turbojet engine design. The U.S. Army Air Corps faced the critical decision of selecting the American company that would be entrusted to bring this revolutionary technology to production. Strikingly, they did not immediately call upon a traditional aircraft manufacturer. Instead, they placed the call to General Electric. The reason was simple and compelling: the existence of their supercharger department. GE was the singular company in all of America that possessed the unique, hard-won expertise to manufacture and test a turbine wheel that could reliably sustain rotation at 16,000 revolutions per minute while bathed in 1,500 degrees exhaust gas temperatures, without immediately and catastrophically disintegrating. They called Sanford Moss out of his technical retirement. Moss examined Whittle's intricate drawings, a profound smile creasing his face. The gas turbine, the revolutionary device he had written his own PhD thesis on all the way back in 1903, was finally technologically possible. The mechanics of the new jet engine were, to Moss, almost identical to his turbocharger. In the turbocharger, the energy-releasing combustion event happens within the piston engine cylinders. In the newly conceived jet engine, the combustion happens continuously within a specialized combustion chamber situated directly between the compressor and the turbine stages. Moss's highly skilled team at GE took their proven turbocharger technology, the high-strength stellite turbine blades, the meticulously perfected compressor aerodynamics, the critical understanding of thermal management, and used them to construct the General Electric IA, the very first operational American jet engine. The identical technology that had allowed the B-17s to fly higher than their enemy was now the foundational technology that enabled the P-80 Shooting Star to fly exponentially faster than any piston-powered machine. The turbocharger's modern legacy. The profound legacy of the turbocharger, however, did not exclusively ascend into the sky. Its power, its efficiency, and its engineering principles also descended directly onto the nation's highways. For decades following the war, the turbocharger was widely regarded as an exotic, complex, and high-maintenance piece of aircraft technology. Too hot, too fragile, and far too expensive for the mundane requirements of mass-produced automobiles. Then, a new technological wave arrived, the diesel revolution. Commercial trucks required immense torque and pulling power, but the large displacement engines traditionally needed to achieve this were excessively heavy and consumed vast amounts of fuel. Engineers immediately recalled Moss's critical lesson: waste heat is a source of free, recoverable power. They began strapping robust turbochargers onto standard diesel engines. Suddenly, a relatively small six-cylinder diesel engine could generate the necessary torque to efficiently pull a 40-ton articulated load up a steep mountain pass. The turbo diesel rapidly became the reliable backbone of global logistics and commerce. Today, observe the car sitting in your driveway. It is highly probable that it is powered by a modern, downsized engine, perhaps a 1.5-liter or 2.0-liter four-cylinder unit. Just 20 years ago, an engine of that modest displacement would have been considered weak, suitable only for low-power applications. Today, however, that same small engine reliably produces a formidable 250 horsepower. The silent, ubiquitous reason is the turbocharger. We are no longer utilizing them primarily for the arcane purpose of achieving high-altitude flight. Instead, their modern application is focused squarely on thermal efficiency and power density. By meticulously recovering the thermal and kinetic energy from the exhaust gas, a turbocharger allows engineers to make a physically small engine perform with the powerful feel and torque characteristics of a much larger one. This means we burn significantly less fuel volume, yet we extract the exact same level of power and performance. A generation of automotive purists still stubbornly adhere to the adage that there is no replacement for displacement, advocating for large, naturally aspirated V8 or V10 engines. Yet, the undeniable reality of modern, global engineering asserts a different truth. The turbocharger is, in fact, the most efficient and powerful replacement. This compels a final question for the enthusiast. On which side of this great divide do you stand? Are you a proponent of the naturally aspirated, large displacement philosophy, or are you a dedicated advocate for the high-efficiency, forced induction power of the boost? The lasting legacy of Sanford Moss, the man who tamed the high-altitude engine, continues to shape the world we drive and fly in. Don't forget to subscribe and hit that notification bell for more content like this.